Let's have a look at a concept that we learned in grade 11 called Oersted's principle. Oersted basically stated in simple terms that an electric current moving through a conductor, say like a wire, induces a magnetic field around the conductor. So basically, what he was saying was that electricity or electric current causes magnetism. An electric current produces a magnetic field around the conductor. So that means that any time electricity travels through a wire or any kind of charge travels in any way, it will produce a magnetic field. Now the typical way that you see this drawn is you'll see a conductor or a wire drawn like so, and indicating the direction of charge or flow. So we'll use conventional current, positive to negative, which means that the current direction on this conductor is from bottom to top. And then the magnetic field is usually drawn. Now the problem is, of course, it has to be drawn at right angles, and so it's hard to do it. It's a 3D picture on a 2D sheet. So we tend to draw the circles something like this to give the impression that they are sort of sticking out of the board. They're on a plane that is perpendicular to the screen that you're looking at right now. And of course, we have what's called right-hand rule number one. Right-hand rule number one, which basically tells us that if you use your thumb to be the direction of the current, or the direction in which the charge is flowing, so we'll call that current direction, then your fingers, as you grasp the wire or the conductor, your fingers wrap in the magnetic field direction. Because remember, magnetic fields do have direction. Even though it's hard to visualize anything actually moving along the field, because they don't quite work that way, unlike electrons, which are moving along wires and things, they do have a direction. And that direction can be found with right-hand rule number one. Excuse me. It's difficult for me to show you exactly what that would look like on the board, but I will make an attempt. So basically, if your thumb is lined up this way, there's your thumb, and your fingers then are going to wrap around the wire. So what it's actually going to look like is your fingers sort of wrapping this way. Here's one finger, and here's the other finger, and 3 fingers, so let's make it 4, your baby finger, and of course this is the palm of your hand, here like this. And so the conductor, or the conductor sort of sits in between the wrapped fingers of your hand, something like that. So you see how your thumb is pointing in the direction of the current, and your fingers are wrapping in a way that goes around the back and then out across the front like this. So crossing left to right in front, but dipping behind the wire. And so I've tried to draw that. You'll notice on my picture, I've drawn that where it's coming out in front. So we could put little arrows, say here, to show that it's going out of the board and over the front, left to right, and then down, tucking in behind, right to left, sort of that way. Right? So if you were to look down from the top, you would see this as counterclockwise. If you were to look down from this view right here, from the very top, what you would see is the wire sort of this way with the electricity going away from you. The board's not very well lined up, so my small pictures get... So let's try it like this, with the board moving away from, the electricity moving away from you. And you would see the magnetic field lines looking like this, nice and circular now, and they would be moving in a sort of this kind of a... Oh, I'm sorry, wait a minute. Not moving away from you, I just realized that's backwards. If you were looking at it from the top, you would see the electricity coming towards you, wouldn't you? So there's the wire, and in it the electricity is coming from, so a dot means that the electricity is coming up out of the board towards you, right? And you would see then a counterclockwise sort of field. So those are the two different ways in which we can visualize this field. Some interesting things about it. You have to understand that although the picture looks like it's in one spot, these red lines extend all along the length of the conductor. So really, it's kind of like giant sheets, right? Think of the red line as instead a sort of a sheet of paper wrapped in a circle, like a cylindrical type of shape. It's hard to draw all those red lines in this kind of a picture, but it's more of a spherical, cylindrical type shape that goes all around the conductor. Okay? So that magnetic field is present at every point. I can draw the same little set of circles at every spot on this wire, all around like this. And then you can see how, if your eyes are really good, you can see how all those lines would form a sort of a cylindrical shell around it. Now what's important, of course, is how far out you go. Because we know that the further you go out this way, away, the field gets weaker. So inside here, you'd have a stronger magnetic field. But away out here, you'd have a weaker magnetic field. So the distance away from the conductor is very important. All right? And another thing that is very important is the amount of current that is flowing through the wire. If you have a stronger current, you'll get a stronger magnetic field. I guess I should say a larger current. A larger current would give you a stronger magnetic field. A weaker current or a lower current would give you a weaker magnetic field. Okay. Now there are a couple of other things that affect this field, and maybe we'll start talking about that, because that was the end of grade 11. But what you want to do now, of course, in grade 12, is you want to sort of say, that's great, we know which way it goes, we can draw cute little circles, but what is an actual numerical value? Can we figure out the magnitude, the actual magnitude of this force using some mathematics? And that's the part we want to go through now. Now the mathematics are a little bit complex. So what I'm going to do is I'm going to show you a couple of equations that describe these magnetic fields. And we're going to take a few liberties, because some of the math is a little complex for us to understand. And we're going to take some liberties in developing an equation that we can actually work with, something that's relatively straightforward. So, to describe the magnitude of magnetic fields, let's look at the factors that affect the strength of the magnetic field. Well, I'm going to draw a second picture here, okay? I'm going to draw a picture that looks like this. Here's my conductor. And I'm going to try to draw my magnetic field sort of around the conductor. Let's do it like this. Okay, so it's just kind of a tipped over version of what we had before. All right. Now, as we said, if we take a point, any spot, let's pick a spot right here in green, call it the point P, and we want to know how strong is the field, the magnetic field at that point. Well, the magnetic field is going to be based on a number of things. It's going to be based on how long of a segment of wire we actually take. Okay? If we take a segment of wire, say this long, call that the length of wire, right? Well, then we have to look at the angle that length is away from the point P, that small piece of wire, right? That angle, of course, if you're right underneath, if you picked a tiny spot right in here, well, then that angle would be 90 degrees, and it would give you the strongest possible value. But if we took a segment, say, over here, right, and I'm drawing a big segment, so you wonder why, wouldn't the angle be different from the front and the back of the segment? I'm drawing a big segment just so we can visually see it, but generally in math when we do this, we pick very tiny segments, right? And we use the magic of calculus to help us get where we want to go. So we want these little segments to be very small. So generally there wouldn't be any appreciable difference in the angle. The other thing that matters, of course, is the amount of current. So I'll put that in green, red, what do we got here? How about purple? So the strength of the current that's in the wire, or the amount of current, is also going to matter big time in terms of what kind of a field strength we get. And the fourth thing actually that matters is something kind of new, which I will draw in, I guess I'll draw it in red over here. We give it the symbol mu. A lot of things are called mu in physics. We've seen it as a coefficient of friction. Here, it's called the magnetic permeability. Magnetic permeability. Now, the last time you've seen the word permeable is probably in your biology class with semi-permeable membranes, right? And it has this idea of allowing things through. If something is permeable, it allows things through it. And you can kind of envision this to mean, in a way, how easily a substance allows magnetic field lines through it. How easily a magnetic field can be set up inside this particular substance or matter. Now, if we consider it to be a vacuum, we generally give it a little zero, mu naught. And that's the magnetic permeability in a vacuum, the vacuum of space where there is no matter. And it has a value of 4 pi times 10 to the negative 7. And it also has a unit that goes with it. The unit is basically just designed to work with the formulas so that everything will work out great. And the unit, I think, is a Tesla meter per amperes. So it's Teslas dot meter per ampere if you want to know the unit that goes with it. Typically, though, we just understand that these numbers are already designed with the proper units in them to give us what we want, so we don't sweat them too much. Now, that's for a vacuum of space. It turns out, though, that most substances that we are accustomed to seeing magnetic fields form in are actually not much different than that. For instance, if you want to form a magnetic field in air, which happens to be the substance around my conductor that I've drawn in my picture, it's just air all around it, then that value is pretty much the same as mu naught. We can use the 4 pi times 10 to the negative 7 and not sweat it so much. It's different by a very tiny fraction. And a lot of things are similar to this vacuum value of magnetic permeability. The things that are not are the obvious ones. Air, things like wood and plastic and stuff that doesn't magnetize, right? The reason it doesn't magnetize is because it doesn't have a very high magnetic permeability, among other things. But things that do are things like iron, our good friends, the ferromagnetic metals, nickel, and even cobalt. And we've been able to use these metals in alloys with other metals to make even more powerful magnets. But iron, if you get really good iron, and you do it carefully, in a very careful process, you can get something where it's 5,000 times more greater magnetic permeability, 5,000 times that of, say, in a vacuum. But how many people actually ever find themselves inside iron? And so most of the experiments we do and most of the things that we look at and the pictures we draw, it's all just air all around here. So for now, we're just going to worry about this number right here as the magnetic permeability of air. That's going to be the number we'll use if our magnetic fields are forming in the air around a conductor. Now there's a guy by the name of Biot, French guy, B-I-O-T. And he came up with a relationship. And he said that the magnetic field at any given point will be equal to the magnetic permeability multiplied by the current times the length of the segment of the conductor, and sine theta, which is the angle at which that conductor meets from the point, divided by 4 pi r squared. And the 4 pi r squared is kind of telling you a little bit about the fact that it's a circular shape, right? Because at the point P, I could continue that point P, and it would be the same picture all the way around this circle, wouldn't it? Because this circle is the same distance away. So technically, it's not just the point P, it's also the entire circle all around there. And of course, the R is kind of like the distance here away from the point. Now, we can do some simplifications of Bohns Law. In fact, that's what this is called, Bohns Law. And these simplifications are done, they were done by applying something called Ampere's law. And Ampere, whoops, wrong way, accent goes the other way. Ampere is another fella, André Marie Ampere. And Ampere's law can be used to simplify Bohns law. And what Ampere did is he basically found a way to restate the length of this conductor and this number on the bottom in terms of some other stuff. Basically by imagining tiny little lengths all around the path of this magnetic field. He imagined little lengths all around here, and he was able to show that the sum of those lengths works out to a couple of expressions and so on. So rather than get into those details, I'm just going to show you that through the magic of Ampere's law, we can reduce this formula to something a little simpler, something that we can use that's a little easier. And it's B, the magnetic field strength, equals mu I divided by 2 pi r. Now I have to make sure we understand what these mean. So for this simplification, we've got a few things that are a little bit different. The mu is still the magnetic permeability, right? And I'm going to draw one magnetic field line here. And so the point right here on this field, if we take r to be the perpendicular radius right in there, r, okay, then the field strength at that point, and in fact, not just that point, but at any point all the way around this circle, because all of these points are the same radius r away from the conductor, aren't they? And so that's the r right here that we're talking about in this equation, how far out we are from the conductor. And then the magnetic permeability, mu, of course, is still the same thing. It's the magnetic permeability of air, and the I is the current flowing through the conductor, and then the 2 pi. And the 2 pi r is just basically giving you the circumference of this circular shape. And so this is an easy way to find the current, right? Sorry, not the current, to find the magnetic field strength, or the magnitude of the magnetic field, at a point a perpendicular distance out from a conductor. Really cool. Okay. Now, of course, conductors can change their shape. Wires are not always straight. And so what basically happens is, we take Bohns law and we can mess with it by using all kinds of tricks of math and geometry and calculus. And we can discover expressions that will help us find the strength of magnetic fields in different variations. So we have one here. I'll call this one number 1. Right, there it is. That's for a straight conductor, and it works pretty well. We can also take a conductor and we can twist it up into a coil. Now, there are two kinds of coils. So let's see what happens if we talk about coils. There are two kinds, basically. There's what we call a flat coil, right? And there's what we call a long coil. A long coil is also called a solenoid. Now, what's the difference between a flat coil and a long coil? Well, it's a little bit arbitrary. It's kind of a little bit of a little bit of guesswork. But let me show you the difference. I'm going to draw a flat coil, and I'm going to draw these. First, what I'm going to use is an imaginary sort of core here, because this core is usually just air, or it could be metal, it could be a metal core, it could be anything. So I'm going to show you this, which will be a flat coil, and then down here I'm going to use this to be the long coil. All right, now it's all on how you wind the wire. So I'm going to wind my wires in green. I'm going to start down here, and I'm going to wind my wire all the way up like this in front, down around the back, and then back up the front, and then down around the back, and then out again from the behind. Okay, and there. So I'll make this a little, there's my current direction in my coil. There's my coil. What you will notice is that the coil is circular, and the radius of the coil, if this was the center of the circle, this would be the radius, R, of the coil. And the length of the coil is simply how long the length of all the windings. So there's my length of the coil. And what you'll notice in a flat coil is that the length is small compared to the radius. Excuse me. The length is small compared to the radius. Okay? So generally, in a flat coil, the radius is the number that matters most. It's much bigger than the length, and the length is sort of insignificantly small. And in a long coil, you would wrap like this, up over the top, down around the back, up over the top, and so on, down around the back, up over the top, up across the top, and all the way down, and all the way across, all the way down, and then down to the back, behind, out, hook it up to a source of voltage to get current to flow, and there's your coil. Now, the R is sort of like this distance right here, the radius of this coil. If you were to kind of look at it from the end, you'd see it was a circular shape, right? And the length of the coil now, you'll see here, is quite large. So it's the opposite. A solenoid or a long coil is one where the length is large compared to the radius. All right? In this case, these coils are longer, and it's the length of the coil that matters more. The radius isn't so much an issue anymore. And so by using some clever mathematics, which we won't get into, we can do the magnetic field strength for a flat coil, right? Flat coil. And incidentally, a flat coil can also be, it can include a single loop of wire. That's a single loop of wire is often a flat coil, because if you think about it, one loop of wire, right? Well, the length of that coil is just the thickness of the wire compared to the radius, which is quite large. So usually a flat coil or a single loop are treated kind of the same. And so through the magic of the math, we can change the equation for the field strength, the magnetic field strength, into one that looks like this. Mu N I divided by 2 times R. Now, this R is a little bit different. This R is the radius of the coil. Because remember, we said in these coils, if we go back up to the top, the radius is the thing that matters. It's the bigger number. It's important. See how the radius is larger. So this is the radius of the coil, right here, the radius of the flat loop or coil, or the single loop of wire. We still have the magnetic permeability, mu, we get that, and we still have the current, which is that. The number 2 is just 2, but the N stands for the number of turns in the coil. If the coil has 1 turn, 1 loop, number of turns, or I guess you could say loops. So this coil here has 1 loop, but if I go back to the coil that I drew, you'll notice that it goes around twice. It loops around right over the top, down around the bottom, then over the top, down around the bottom. So it would have 2 loops. And you can have 5 loops, or 16 loops, or 100 loops. If you have a large coil, large radius, right? I could take a wire and I could wrap it several times like this, over and over and over and over and over and over and over. Of course, the more wraps you get, you tend to get a little bit thicker length. but still the radius is much bigger. So a flat coil, that's how you do it. And then if you have the solenoid or the long coil, the solenoid, then O-I-D, solenoid, then what happens is the rule can be changed into B, and this time it's not the radius that matters, it's the length that matters, and so you get N, and then you get I for the current, and you're going to divide this time by the length of the coil, right? The length of the coil. So for here, you have to remember that this is our R, the radius of the coil, and the current, and then the number of turns, except over here, we don't want that. We want our coil like this, which is going around. I'll draw it without a core this time, just kind of, there's our coil of wire, right, coming down here, whatever the current would be. So we want the length of the coil this way now. How long is the coil? That's our L. And N is, again, the number of turns. The number of turns. So now you have, basically to summarize, you have three ways to calculate the magnetic field strength. You have a straight conductor, mu I over 2 pi r. Then you could write down, this is for a straight conductor, straight piece of wire, right? Or you could use B equals mu N I over 2r, right? Mu N I over 2r, and this would be the one you would use for a flat coil, where the radius is more important than the length. And then you also have the option of B equals mu N I over L, which you would use for a solenoid. Whoops, solenoid. I think I can spell that by now after I've written it 3 times. Solenoid, right, or a long coil, where the length of the coil is more important than the radius. Mu N I over L. Okay, and then it's just basically plug and play, and don't forget that the value of mu is, for air, pretty much 4 pi times 10 to the negative 7, and you'll plug that in. That won't change much. Now if you embed your wire in a big chunk of iron, then obviously you'd have to use a different mu. If you put your wire underwater, you would have a different mu, but guess what? That mu is almost the same as this one too. So it really doesn't make a huge difference. And so most of the substances in which we find wires will not have a mu that changes much. But if you wanted to be precise, you would have to use the appropriate mu for each substance that the wire was in, but we'll cheat a bit and we'll use this number unless specified otherwise. Okay? So we will assume that we're talking about a substance that has a magnetic permeability very close to the vacuum of space, and usually it will be air. And so there you go, 3 formulas to use that you can now put a magnitude, right? And of course the direction can still be determined by the good old right-hand rules. And we've done that before, so we don't have to worry about that. The directions using all your right-hand rules. If you wanted to do a review of right-hand rules, what was I doing? I was going back to the pictures here. You could apply the right-hand rule to the solenoid and to the flat coil, and you could apply them all to get the directions of the magnetic fields without a problem. So these formulas are just telling us the magnitudes. And that's the end of today's lesson. And next time we'll look at some of the cool things that happen when electric charged objects move through magnetic fields on their own without a wire. And I promise you it will be very exciting.